Um, so winding down. Okay. Exam the finals Thursday. We'll have a quiz today. We'll have a quiz on Tuesday. Wednesday will be a review session. Final exam Thursday, 8:30. Who has an exam that day after my final? The final exam will be like 100 points. I think that's what most of that. So it's sort of like a bonus points on exams for work. It's sort of like I got 10 bonus points I put in there. So the exam okay. So here we go. Last couple of days, of course, nothing new to cover. What do you guys questions? You guys, what worries you most about the final? The stuff we just learned. Okay. Actually, it might be a good idea to kind of go with quiz. I could probably put that up. Let me ask you this about the quiz here. Yes. Okay, so share screen. Yeah, like I said, I'm sorry I didn't bring it. This is values. Very honest today. They're right and all. So, what do you think? What was the hardest one on there? How would you do? How would you do A? What's strategy for A? Okay, so what technique? I think you're on the. I think you're on the right track. What technique are you doing there? Yes, yes, she's right. Parts. So if you have something like this, so if you do this right here, the inverse tangent thing, that's a big hint. You see logs, inverse tangents, logs, very low parts. And also, I would say good use of U equal X never works, right? U equal X would just change all this into U's and just by itself, U is inverse tangent. I don't have any the answer. So let's take that advice. Biggest ugliest piece I can integrate in my head is this. I know the derivative, but I don't off the top of my head understand that derivative. And there's your pieces parts. So step one, put this back together again. 1/2 x squared inverse tangent x minus 1/2 x squared over 1 plus x squared. Now, right? I'm liking this integral better because it's just proportional polynomials, but I still got to know what to do with it. Any ideas on that? Actually, it's from substitution, and I showed you back when we did substitution. We'll work on this too, but you'll beat that to death in 80, but don't do it. There's an easier way to do this. So let me do a little algebraic massage. Look at this function here. That's what I'm trying to find the answer to. Right? I want to use a little bit of algebra, not too much, a little bit to write this in a easier to digest. Okay, how many times does x squared go into 1/2 x squared? What do you got to multiply x squared by? You get 1/2 x squared. Half. So this is 1/2 x squared plus 1/2. And just like you're back in grade school, when you want to baby, subtract it. It makes that sound. You minus 1/2. How many times does x squared go into this? It doesn't anymore, right? Because the degree of x squared is 2 and this is 0. So yeah. I might say that this is my quotient is 1/2 and the remainder is minus 1/2. What that means is I can rewrite this now as the quotient, but it doesn't divide evenly. It's the remainder over what I divided by. And you can always again check yourself by putting this back over the common denominator, x squared plus 1, and you should get back. Right, let's check. This is x squared plus 1. Let's see, put this over that denominator. I get 1/2 x squared plus 1/2. Right, notice 1/2 cancel. Right now, so that piece is correct. Plus negative 1/2. These two cancel out, and I get my. Everybody okay with that? But it's much easier to integrate this. And let's see why. One. And now I've got two pieces both of which this is 1/2 x squared inverse tangent x minus 1/2 x plus 1/2. What's the derivative? 1 over 1 or the antiderivative 1 over 1 plus x squared is the inverse tangent. Any question? Yes. What's that? Well, that's just simple, right? I mean, I really wish I could give you like a recipe that would always work. Unfortunately, no matter what I give you for a recipe, I can also construct something that can work. But so you have some things at your hand, and then once you get to this point, you do a use substitution. But it's not really clear what to do. The substitution they will work, but that's beyond what we're really doing in this course. So another thing to do is to think about writing an algebra. If you can factor things, hands on factors, to okay. What about this one? About what do you think about this? What technique might? Yeah, both. I think that's right. This one will actually yield parts, but taking the derivative, well, you can't take the antiderivative. It's problematic. Take the derivative of it, but it's got that obnoxious chain. Sometimes it's good to sort of cosmetically change this. Anybody see a use substitution? It might work to make this a little bit simpler. Very good, very good. I'm gonna call it Z here, but yeah. Don't you wish that was just e to the x instead of e to the x squared? Well, let's try to make that so. See if this cleans it up. In this case, Z is 2x dx. So if you want x dx, it's 1/2. So let me take one more step before I can change things here. This is just a rewrite of this, right? I pulled one power of x to the dx, kind of keep track of what I've got going on. And the reason for this is this piece is going to be e to the z. This is c. And this is 1/2 these. But okay. So just put my eyeballs on. I've analyzed it. I can turn all my x's and z's. That's good, right? Always make sure that you're taking care of your dx. You can there's only one dc or dx or whatever it is, and don't put it at the bottom. So this becomes 1/2 z e c. And now we're going to have to some parts. It's a little easier. What's the biggest, ugliest piece of that I can integrate in my head? I agree. And so what's left over is 1/2 z. So U is 1/2 z and d is evens. And using my parts formula and put it back together, it becomes 1/2 c e to c minus 1/2 e to c. I love that. Right now, let's turn this easily. There you go. Oh, but I'm not doing it. What should I do at this point, the problem? Yeah, I've got this in terms of C, and it's correct, but I really should get it back in terms of my original variable X. And let's see, what do? I replace every Z I see with X. So this is here 1/2 X squared e to the X squared minus 1/2 e to the X squared plus any questions? Okay, what about this one? How you gonna do your parts? That's good. Let's try that. What's one thing you did notice? Okay. And you know what I'm gonna do? I'm gonna do X cubed minus 1. And the reason that I stuck the extra constant on there is because it turns that into one piece. And it didn't hurt me because when I take the DZ, it doesn't matter whether it's X cubed minus 1 or X cubed, you're still going to see. So I gotta get that thrown off for now. Well, everybody agree with that? Okay, now I want you to put your eyeballs on that and tell me, what am I going to do? Right, because I understand what's going to happen under the radical. That's my substitution. But I'm a little bit befuddled by the X step. Okay, so. And how does that help? Y'all see what you're saying? This right here. That's another way with our substitution. And let's see what we've got. X squared dx is X squared dx. X cubed minus 1. This leaves me with an X cubed. Everybody agree? Oh, so this is awesome. Because this is 1/3 dz. Yes, right. This is z to the 1/2. And this is z plus 1. Oh, so this is the same. This is z 1/3. Z to the 1/2 plus 1. Right. Now what? What's that? How do you want to do your parts? squared. I think you're gonna. It doesn't have to be hard. This one, I know. Yeah, don't be afraid of now. Look, it's multiplied out. And that's what I want to do, because now all the powers of city, I can do that like that. Right. So do that when you, that's the beauty of it. Square root up here is what's killing you. When we make this move and put the square root into a single term, and I can multiply through, that's much easier. Okay, we'll file. This is z to the 5 half over 5 halves. Says 2/15. Z to the 5 halves. Let me check it real quick. 1/3. This is z to the 3 halves of 3 halves. So 2/9. Z 3 halves. Let me check that. 1/3 is 1/2. Finally, last thing you did, we put my. And z was x cubed minus 1. And again, you probably don't have time for this doing the quiz the other day, but when you do your homework or whatever, you can always check your work on taking the derivative. You back where you started. Okay, questions? Okay. Okay, first question I'm gonna ask you next, general strategy. What are we gonna do? What are you gonna substitute? Yes, maybe I will do this. So x, so you're gonna go, what, z is log x, such as but what am I gonna do for this? Right, I mean, I can't argue with that. But you got some fixing to do, because over here, you're mixing and matching, right? You gotta. What's another name for x? There you go. This one's actually solving. So yes, you do your magic. See. Everybody following? So if I implement this thing right here, like log x squared, c squared, and my dx is e to z. Whatever. This one is probably a little bit more recognizable parts. Do I agree with it? So let's bring this over here. So there you go. 6 squared. I'm gonna do parts. And it looks to me like the most complicated piece of this I integrate is that exponential. And that leaves you c squared. So du is 2z z. D is good old e to the c back at you. So this becomes z squared z minus 2z e to c z. Now, I can pull that 2 out of here, but again, I recommend making part of it. I've made myself better, but I'm still stuck. What should I do now? Do it again. Have patience, little soldier. Keep going. All right. So this is u is 2z, and d is e to z dz. Same tactic we did last time. And du is 2. So this now becomes we'll see, we've got 6 squared e to z hanging around. Minus, this minus is always kind of throwing me when you be careful here. Product this whole thing breaks. Product of these two is 2z equals minus 2e to c. So I get z squared e to z minus 2z e to z plus 2 e to z. Right, okay. And what do we got to do now? Let's see. Everywhere. I can just put log x in there for a CSC. I'm gonna make it convenient. Notice that e to the z is x. I mean, if you put log z in, you get e to the log x. X, right? So this actually turns out to be x log x squared minus 2x log x plus 2x. That's I know what it is. Okay. Come again? For this one? Well, that should be it, I guess. Right? Derivative of x one, so that's log expressed in 2x log x. Let's see. Here's log x. Let's see here. This is c squared x is c here. C squared. X squared. Oh, right. So derivative of this log x, I think the derivative of this is 2x log x, it's 2 log x. Cancel by that, minus 2 log. Right. Log x. Minus 2. That's let me do this another way. We could have done this correctly. Follow this. So it's almost always more than one way to do this. This one get the answer, I think, with a couple of steps. If I tell you to use parts on this, you pretty much have no choice, right? Because there's nothing really that I can do. And du is 2 log x over x. Everybody understand that? And something really nice works out here, because what you have is parts gives you this times this minus the involved product. And look what happens here with the product. This x cancels that x and y. And I get plain old 2 natural log of x. So that's convenient. That x kills that x that I got from the chain rule at the bottom of that bottom left action. So now I'm going to do parts again, same strategy. U equals 2 log x, and d is dx, d is x, and du 2 over x. So this is x natural log x squared, and then minus, let's put this all in braces so that we can track out of it. Minus this product here, which is 2x log x, minus 2. Last product being is 2. And so this is x log x squared minus 2x log x plus 2x. That's same answer. So that's strong evidence that we did this right. Any questions? This is the one that I kind of mouthed off about. I said, oh, this one's easy. I guess it's easy when you see it. I guess they're not business. Secant squared sine This is a one stepper if you see. What is it? Anybody? What do you do on this problem? Okay, what are you going to substitute? Good. So the inspiration, I don't want to put words in your mouth, but the logarithmic diffusion is exactly what it is. Part of the inspiration. So this is sine of u, sine of u part right there, and what's left over is just good old the. What's the antiderivative of sine? Negative cosine u minus cosine tangent x. How about this? I want to give you a hint on this one. Just like number D, you can do this a couple of ways. So if you do the Emery substitution, you do the log x, this will do, and it'll turn it into an exponential sign. It's plain to just go ahead and try it real quick. It's fun. If I tell you what to do parts, what makes this a little bit easier is you ain't got no choice, really, what the parts will be. U is my big fat blob, this is going to earn there. And ED is units. And we get some similar stuff happening that we had before. So du is cosine natural log x. I'm derivative of natural log x, 1 over x. And b is equal to x. So this becomes x sine natural log of x minus, hold on, let me on the cross. Minus cosine of x. So u is cosine natural log x, and b is x. So du is cosine minus log x, of derivative log x, is x. So this now becomes again, let me be careful. Minus this whole mess here. That's going to be x log x minus cross it minus sine log x. Clean this up a little bit. This is x sine log x minus x cosine log x minus, so minus sine log x dx. And what do I do now? Okay, that's sort of it. So this is a synopsis of where we are right now. We started out with this. We started out with this. And we ended up with this. That's what we do. So what do we do? Right. Treat this like an algebraic equation. We're looking for Fred, and Fred is this minus Fred. So bring this over. And now I've got two Freds on this side. Is x sine log x minus x. Oops. So all I gotta do is divide by 2. Take 1/2 x sine log x on 1/2 x cosine log x. So it takes some getting used to practice substitutions and parts of business. The good thing is for 99% of problems, there's only a couple things. So have the courage to try some things, fail on it if it's not working, and try something else. But don't necessarily bail on it too quickly. Number C on the quiz with the radical is good because sometimes you use a substitution for it once to work things out. Okay, other questions? Okay, what else we got? Question on tests. Okay. Okay. So I guess the first appropriate question is, you'll technically be changing in 40, but you also feel comfortable with that? Because that that seems to come up over and over all the way down. You feel like when you look at number 1, where you've got a lot of derivatives, some of these functions are complicated, but you all can tackle it now. Is there anything you look at? How about, just for fun, here's one of the things. Let's do C. Quick. So suppose we want to do the derivative of inverse 2x. Okay, what do we do to do this? Does anybody see a problem on the horizon? What's the most obnoxious part of this? Two x dx squared, somewhere we'll have a problem down the road, is variable base and variable x. Right. But if you're doing the chain rule, what's the first thing you come to here? Yeah, inverse tangent of blah. Right? Do we know the derivative of that? Right, so let's do it. I will literally do the problem this way. Derivative of inverse tangent of blah is 1 over 1 plus blah squared. Ding, ding, ding. There's your first check. And I'll literally write this. This answer is correct, but it is incomplete. Right? Because I will find you to answer this question as well. But at least I've demonstrated that I know chain rule. Don't be shy to take this apart. I will come over here, I will write, work out on the side, on the side here. Find the derivative of that, because that's all I need to finish this problem. Right? Okay, so how do I go about this? That's exactly right. This is always the recipe. When you have a variable base, variable exponent, you got to dig that exponent out. So let's take the log of both sides. And of course, the whole point of this is this x squared natural log of 2x. Now, once I've shaved that exponent down off of this, I've got a situation where I can take the square root of this. So let's dx both sides. What's the derivative of log y? There you go. Good. I'm y prime. Don't forget that. It's fuzzy. What's the derivative of this? It's a problem. Right? So I've got me a 2x log 2x. And I've got me an x squared times the derivative of log 2x. 1 over 2x. Times 2. So I get y prime is y times this mess, 2x log 2x plus x. There's a lot of cancel, which is 2x x squared 2x log 2x plus x. So now, go back here and finish my problem. This is 1 over that's x squared times x to the 2x the x squared times 2x log 2x plus x. Does this look easier now than when you first did it? Yeah, that's so. Everybody understand? Okay. What other texture? Oh, part B up there?
You do delivery.
You don't have to, but I highly recommend it. Right, because that will, you see what you talked about in part B, where we've got x squared and sine of 2x, and t to the x squared, that e product on the bottom. If you take a log of that first, it allows you to write the products as sums, quotients as differences, and allows you to bring down the exponents, and you'll be doing it much easier. You want me to go through B? I've got it. So let's do that. I'm going to do this fast, and this is the point. This is the point of the class. So stop me if I go too fast, but I'm going to show you how I do this quite quickly. G of x is going to take you longer to write down the stupid problem. X squared sine 2x e to the x squared times x plus 1, x plus 2 squared, x plus 3 cubed, and log x 4. Now, you can just go ahead and take the derivative. This is actually something, well, what you do with the derivative log. Did you all learn the derivative log? No. Besides this, you could have done this in board by doing the first option, which you could. I would recommend doing this first. This is 2 on x plus log sine 2x plus x squared minus log 1 plus 2 log x 2 plus 3 log x plus 3 plus 4 log x. I mean, give you a moment to get your breath. Okay. Okay. Is everybody supposed to come from? Basically, just to kind of briefly reiterate, I've got 1, 2, 3, 4, 5, 6, 7 pieces. 3 in the top, 4 in the bottom, with multiples. And taking logs of products and quotients basically turns into sums and differences. So it's log this, log this, log this, minus log this, minus log this, minus log this. Right? And the only thing different that I did is I brought down the exponent. Log of this, that's log of x squared, I bring the cube down. This is plain old log sine 2x. Log of e to the x squared is just x squared. Minus log x plus 1 to the first, minus log x plus 2 squared, 2 down, minus log x plus 3 cubed, 3 down, minus log of blob, log x, and I brought the 4. Even the derivative, this message. And dealing with the original set. Cos was ddx this. Derivative of g of x, log g of x is 1 over g of x g prime of x. And I can take the derivatives of these variables. 2 over x, 1 over sine 2x times cosine 2x times 2. Change of imaginary. 1 over log derivative. Derivative of x squared is 2x. Derivative of log x plus 1 is 1 over this times 2 over x plus 2 times 3 over x plus 2 minus 4. See, derivative of log is 1 over and so g prime of x, g of x times this mess, which equals x squared sine of 2x e to the x squared over x plus 1, x plus 2 squared, x plus 3 cubed, log x 4 times 1 minus x plus 2 x plus 2x minus 1 over x plus 1 minus 2 over x plus 2 minus 3 over x plus 3 minus 4 over x log x. Close parentheses. Much easier than with the chain rule. Yes.
So you have 1 over sine squared times 6. What is it times 2?
The 1 over sine x comes from log, and then the cosine now times cosine log, now times derivative in all of it. Okay. Okay, other questions? Consider the curve defined by the equation blah blah blah. Yeah, let's see what it's like. So I give you this equation. This equation is inverse tangent something y cubed plus x is equal to sine e x plus. So the question is to find a formula for y. And this formula should depend on both y and x, because I'm not really quite sure what this looks like, but it's probably a big mess. Thing is probably not even a function. So the formula for y depend on both y and x. Okay, so let's just hit this right away. ddx is derivative. Derivative of inverse tangent of log is 1 over 1 plus log squared. Right. Times the derivative, what's this? What's the derivative of y cubed? There you go. Derivative of x is, that's not bad, that's just. Okay, it's the other side. Derivative sine of log is cosine of log. But I'm not done. I got to multiply by the derivative of the sine. In this case, it's e to the x y. Derivative of e to the log is m. And now I'm going to multiply by the derivative of x y. That's the property. So derivative of x times y plus x times the derivative. Now that right there is the big guts of the problem. Everything else from here on out is just out. You've got to, so calculus part of this step is over. Does everybody understand what we do now? Well, what we're going to do now is just kind of sort out what y prime is to solve. So this, if I multiply this out, this is 3y squared y prime over 1 plus y cubed plus x squared plus 1 over x squared. So that's just this on top plus this fraction. I'm going to try to clean this up a little bit over here. Y e to the xy cosine e to the xy. And then plus x y prime e to the x y cosine. Now, procedure that we really want to go through is all the y primes on one side, all the stuff with y prime on one side, all the stuff with no y prime on the other side. So if I do that rearrangement here, I get like 3 y squared y prime. Okay, so that. Then I'm going to bring this over to the side. Minus x y prime e to the x y cosine. Now on the other side, so I'm going to have y e x y cosine x minus that is 1 over one plus y cubed plus x one. So far. So notice I can pull a y prime out of this. So it should be the right hand side. Divided by this factor. So I pulled the y prime out of this. What's left over that I divide by 3y squared over 1 plus y cubed plus x squared minus x e x y cosine e x. And there's your formula. Please don't try to do anything. That big. Okay. Okay, what else we got? You don't feel comfortable with related rates problems? Let's look at number 4. Yeah, let's take a look at lead rating problems, 'cause that's one of the most important things. You have to practice with lead ratings optimization. In these problems, the calculus is usually easier than this kind of stuff right here. The variables aren't as hard, but it does take a lot of practice to set that. Let's look at number 4 first. The sun is directly overhead at noon and sets at 6 p.m. So that sounds like a factor that I might use later. Sun is directly overhead at noon and sets at 6 p.m. Okay, so that's probably a factor. I've got a. Okay, so I'm observing a shadow of a 60-foot tall flagpole in the middle of a parking lot. How fast is the shadow of the flagpole lengthening? Okay. How fast the shadow of 60-foot like lengthening? And again, this is another one of these things, this is the kind of thing you might not be part of the major shadow flagpole. You're going to do things like this when you're an engineer. Eyeball your answer. Does it make sense? Right? I mean, if we work this problem and we find that the shadow is moving at 20 miles an hour, there's probably something wrong. Would you agree? I mean, nobody's ever seen a shadow moving that fast at 4 o'clock, right? Although, before sunset, there should be some. Okay. What should we do? Absolutely draw a picture. So, what are my players here? Well, certainly I've got the pole. And the sun's up here somewhere. And the sun casts a shadow. Now, what should I be labeling? I mean, it's a very pretty triangle. I'm right proud of it, but it is a bit barren, isn't it? Okay, yeah, the height of the flagpole, that's important. What should I label that? That flagpole never changes in height throughout the problem. 60 is safe. I always 60 feet there. What is changing though as the problem progresses? The shadow. Well, that's right, the length of the shadow. So I think I should be measuring this. I'm going to call this S for shadow. Okay. What else? Right. Time is definitely going to come in, right? Yes. I'm not quite sure how I'm going to reflect it on that picture. You got to keep that in mind. What else in this picture changes as the problem progresses? What's it? The shadow lengths, but what else? What else is changing? I mean, because that's changing. As the sun sets, what's happening to theta? It's decreased, right? When it's almost up at noon, theta is almost power to 2, right? And then as the sun goes down, the shadow gets longer and that angle starts getting smaller. Everybody understand? And that angle is 20. Okay, so let's see what we're doing here. My quest What is my place? What am I looking? What's the answer? That's exactly right. The way I expect the cause of answer. The shadow should be getting longer. At 4 p.m. I need something more. 4 p.m. Certainly, that's what it says here. How can I relate that 4 p.m. to something I've got labeled in my file? There you go. There you go. So let me kind of do a little table here. At noon, what's theta getting closer and closer to? It is. What happens? What if the sun's directly overhead at noon? What do you say about the shadow? There shouldn't really be. And so as you get very, very close to them, what is this angle be closer? How would you I agree with them? At 6 p.m. What's that getting close to? Well, this is hard to imagine, a little bit harder to imagine. As you get close to the sun setting, the shadows getting longer and longer and longer and longer. Like maybe it's 100 miles down the road. Well, that angle is going to be almost even. Right? How does that help? So let me ask you this: what is theta? Yeah. So theta T is it's actually negative. We changed, we dropped power to 2 radians 6 hours. Right? So this is minus pi over 12 radians per hour. Everybody okay with me? That's my observation about the sun and what's doing today. Good question. It changes. What's my change in theta? It changes the same rate. Power to 3 radians negative goes from power to 2 down to 0 and it stands 6 hours. So it's minus power to 12 radians. Okay with that? What's theta at 4 p.m.? That's right, because you're taking away from power instead. Should be negative. Should be the angle should be positive. Remember, you're starting here. So I think so. What you're saying 4 hours, right? And so it should have gone minus power to 3. But you started power 2. So what's power 2 minus power 3? 6. Here's another big one. It's very quickly. noon, 2 p.m., 4 p.m., 6 p.m., right? Every 2 hours, it should go about 30 degrees, right? So at 4 p.m., you're 30 degrees above something, so you're right, okay, so everybody clear on the d theta dt and what it is? Now, the SDT is what I want. I've got a bunch of crap about theta and d theta dt. I need an equation that relates S and theta. What do you think? By the triangles and points. S and theta. How about that? And let's see here. Well, let's DDT this thing. This becomes secant squared theta. D theta dt is, this is 60s to the minus 1, so derivative minus 60 of s squared times ds. Now, what do I have? I know what theta is, power 6, so we figure that out. I know what theta is, figure that out. The only thing I don't seem to know is what S is. I need to know, to use this formula, I need to know what S is. I never figured it out. How can I do that? Everybody see what the problem is? This is what I'm looking for. I've got numbers for this and this. I'm gonna figure out what S is. Shadow. And this would, of course, be shadow of the line. Yeah, just go back to the book. Let's use this equation. At 4 p.m., theta is power 6. So tangent power 6 is equal to 60 over S. Tangent of power 6 when it's 1.3. So I get S is 60 squared. That should be all I have to do. Figure that. Right. Yes. So let's go back and plug everything in. So I get secant squared power 6 times theta t is minus power 12. That's a radian per hour. Minus 60 over s squared. 60 squared times 3. Yes. By the way, there's minus here. It's positive, which is good. Let's see what I get. Let's see. Sort of makes sense. Let's see, the cosine of power 6 is radical 3/2. So on the square of that, you get 3/4, so this is 4/3. Minus power 12 is equal to, this cancels minus 1/1. Yes. The minuses cancel. Yeah, minuses cancel. Let's see. 15, 16, probably something like 25. And this is speed out. And let me see here. Let's see. So this is about 3 feet per minute. So it's about, in about a minute, your shadow. Just a little bit. Yes. Oh, because cosine power 6 is right over here. So secant power 6 is 2 over right. And then okay. Any questions? Does this seem easier to set up now? Just go through the set. Seriously, you draw yourself a picture, label it. That's a big important part, right? And almost all these things would be some kind of triangle or circle or something. How about the planes? Two planes take off from the same airport at the same time. One flies due east at 300 miles per hour, and the other 60 degrees north of us at 400. How fast is the distance between the planes traveling, or distance between them changing 2 hours later? So, what do? Draw a picture. Right? Two planes take off from the same airport at the same time. One flies due east at 300 miles per hour. We call this X. That's how far the plane is coming. And the other one flies 60 degrees north of east at 400 miles. Almost at 60. I'm going to call this. That's a pretty sad looking ride. We have one plane, another plane this way at 60 degrees. Notice I'll label at 60 because that doesn't change, right? These planes aren't. As the problem progresses, so it's great. How fast is the distance between the plane changing 2 hours later? Okay. My picture looks a little bit barren. What if I neglected to illustrate on my picture? Yeah. What's something else I should probably be drawing? And it might help to look at what the question is that's being asked of us. I'm going to call this S, the distance between them. What is being asked of us is find the S T 2 hours later. 2 hours after taking. Correct. Okay, so let's start to get some of this information down. 2 planes take off from the same airport at the same time. Yeah, I've kind of got that. One flies due east at 300 miles per hour. I've mostly got that. What? There's another piece of information in there. Planes traveling due east, 300 miles per hour. I sort of have a little black line drawn that indicates the plane's position. But what else is there? What's that 300 miles an hour going to get? What is it? That plane is making extra at 300 miles an hour. The other one travels 60 degrees north of 8, east at 400 miles. So what's that? Good. And we need to find the STT 2 hours after takeoff. I seem to have used up all the information in the problem. So what do I need to solve this problem? I need an equation. I've got some information about some x's and the STTs and the y. I need something that an equation that involves s, x, and y. What do you think? I wish that were a right triangle, but it doesn't look like it. There you go, log cosines, which will be given if you need it, if you request it. Mind you, that what it was is a and c theta and c squared, a squared plus b squared minus 2a. So let's do that adapted to our problem. For our problem that s squared is x squared plus y squared minus 2xy cosine theta. And here my theta is 60 degrees. And the cosine of 60 degrees. That's so at this point, just take the derivative of this. I get 2s yes, plus 2x the x plus 2y the y dt. And this one probably should be minus the x t y minus x y. Now our quest here is the STT. So I've got to have values for everything else. So I've got to have numbers for all 5 of those things. Figure out what the SAT is. Ooh, I know 2 of them. I know what the XT is and the YT. The XT is 300. YT is 400. But I seem to be coming up short on the others. Oh dear, oh dear, somebody please help. Okay, that's fine. Here's what we're using this 2 hours to take off. X is increasing at 300 miles an hour, right? So in 2 hours, how long is X going to be? 600. And in 2 hours, how long is Y going to be? 800. And that only leaves S. But see, now I know what X and Y are. And so I can put in my numbers here, 600 squared plus 800 squared minus XY, 600. So this is 3,600. Well, 360,000. 640,000 minus 480,000. And that's an even 100,000 minus this, so I get 5. That's great. So S square root of 500. Right. Right. So now we're in a position to be able to put all these numbers in. Let's just see what happens. So this is going to be 2S, the ST, so this is going to be 2S 400 radical 13. The ST. 2X is 1200. The XT was 300. Plus 2Y is 1,600 times 400. I'm sorry. Yeah, that's 400. Minus Y dXT. So that's going to be 800 times 300. Minus X Y dt, which is also. So I get 400 radical 13 ST. This is 360,000. This is 640,000 minus 48,000. So this is also 550,000. By the way, so I get ST is 1,300 which is Okay, any questions? Okay. After the quiz, go home, study, and bring me some questions tomorrow. Tell me what you're concerned with. Yes. I look up my problems, 60. To make sure, I look back at my old tests, make sure that, you know, anything that you missed, make sure that you can do it now. Make sure, parallels are fast. Front load the problems, just do lots and lots of problems. That's what they do. So. Okay, other questions? All right, well, let's do the quiz.